Thank you, and also thank you very much for the invitation. So today I will talk about some models involving non-local terms. So in recent years, to better describe different kinds of phenomena in nature, there are more and more models involving non-local terms. The aim of this talk is to discuss the effects of non-local terms using the following typical models as examples: genetic model with partial panmixia, ecological model with non-local dispersal, and the shadow system of Guillermin-Hart system, so which is an activator-inhibitor system. Generally speaking, in this talk, I'll try to compare either the local parts and the non-local parts in models, or the local models and their corresponding non-local models. So here's the outline. So first I'll talk about those three models, then discuss some ideas in the proofs, especially want to explain how we try to handle the issues caused by the non-local terms. Then some concluding remarks at the end. So first, the genetic model. Here's the genetic model with partial panmixia. This is the model I want to briefly talk about. This model is to describe the evolution of two alleles, A1, A2, at a single locus under the joint action of selection, migration, and partial panmixia. So throughout this talk, I always assume the model is always in a smooth bounded domain and no flux boundary condition if needed. Okay. So let's take a look at each term in this model first. U of xt here represents the frequency of the allele A1. Then 1 minus u represents the frequency of allele A2. The first term on the right-hand side, this is an approximation for short distance migration. Rho of x here represents the population density. I should say normalized population density. The second term on the right-hand side, which is called partial panmixia, it represents the limiting case of long-distance migration. Here's the definition for U bar. Mathematically, J of x here, mathematically I assume is Holder continuous and change signs. It represents the environment selection for alleles. When J of x is positive, it means the allele A1 has selective advantage. When it's negative, it means A1 has selective disadvantage. Here's a parameter h. In this model, we just assume h is a constant between 0 and 1. It denotes the degree of dominance. This actually is a very important parameter in this model. It affects the qualitative properties of the solutions. When h is strictly between 0 and 1, it's the intermediate dominance case. When it's, for example, when it's 0, it means A1, allele A1 is completely dominant. When it's h is 1, it means A2 is completely dominant. So this is about the terms in this model. So without the, okay, this number B, this represents the rate for the partial panmixia. So without the partial panmixia, it becomes a local models. In this case, actually, this model was proposed a long time ago, around 1975, and there's a lot of studies for these local models. See, for example, for the intermediate dominance case, the existence of non-trivial steady states has been studied. Also, later in 2002, the general elliptic operator is considered, which corresponds to arbitrary migration, just a local case. And till 2010, there are some studies, there are some progress made for the complete dominance case. Then when the non-local term, the partial panmixture, is introduced in this model in 2012, first there are some studies for the intermediate dominance case, and recently Nakashima, Ni, and I will work on the complete dominance case. So this part is what I want to talk about today. So I'll try to show you some results we have about existence stability thing, and during the statement of our results, I hope you can take a look. You can focus on the role played by the local diffusion rate and the non-local diffusion rate, small d and small b. Okay. So basically, because the purpose for us is try to understand the interaction between local and non-local diffusion terms here. First, for the
what is your v there? Large v.
Here, this v. What's your point?
What's the means?
Oh, actually I don't really understand this v is some covariance. I don't really understand the meaning of this. It somehow corresponds to the local migration part. But
It's a function of the
oh, it's a matrix. It's an n times n matrix. Yeah. Okay. So when G is the environment selection, when G bar is 0, there's always exists a stable non-trivial steady state for any D and B. When G bar is not equal to 0, there exists a stable non-trivial steady state for provided that D and B are small. This is for the non-existent part. When G bar is non-zero, then there's no non-trivial steady state for either D or B large.
G bar is average of G.
Yes, it's the average. It's G of X times the population density. Here's the U bar, definition for U bar. So G bar means G times rho. The rho is the population density. So roughly speaking, you can think of as an average. Okay. Okay, next. Stability part. You see, U represents the probability for allium A1, and when G bar is negative, it means on average, A1 is in disadvantage, right? So in this case, for all D and B, U equals 0, the trivial case is always stable. So it means in this case, it's possible for the other allium A2 to prevail. So this is a natural result for all DB. And when G bar is is positive or is non-negative, roughly it means like on average, A1 is in advantage. Then in this case, U equals 0 is always unstable. So there's always a chance for allium A1 to survive. So this is about the result. Okay, next. Also, we studied the stability at U equals 1. We can try to interpret the results as before. Also, you'll see here's our result. When G bar is non-negative, is non-positive, U equals 1 is always unstable. So it means the other allium, A2, always has a chance to survive. Okay, so when G bar is positive, the situation is a little bit different. We found there exists a curve. This curve is concave. There exists a concave curve. Below this curve, U equals 1 is unstable. And above this curve, U equals 1 is stable. Okay, I show you this result, but my point is, based on this result, you clearly see for the studies of the qualitative properties of solutions, the local diffusion and non-local diffusion, they play similar roles. That's my point for these results. Non-local partial premixture have similar qualitative effects as a local random diffusion. However, later in the proofs, I'll show you the non-local diffusion does cause some actual difficulty, mathematically cause some difficulties. So this is about the first model. We see something similar. Next model, ecological model. Our purpose here, we try to compare the quantitative properties of the following local model and the corresponding non-local model. Here, U of xt represents population density. M of x represents the carrying capacity. Mathematically, I assume M is belongs to L infinity and non-negative, non-constant. The purpose for these models is to understand the joint effects of diffusion and spatial heterogeneity in population dynamics. So first of all, you see, this is a classical random diffusion. Here is changed to the so-called non-local diffusion, a simplified one. So first of all, I want to briefly explain something about the non-local diffusion. These are non-local operators. So in general, this is a very general case. Suppose U of xt, that's a population density. This is the rate of change. Then on the right-hand side, alpha of xy represents the probability distribution of jumping from location y to x. So the first term here, it takes account in all the population arriving at location x, right? Then, so jumping from y to x, so all the population arriving x are included here. Then minus all the population leaving location x, jumping from x to other places. So this is the so-called non-local dispersal. Then, in particular, corresponding to the normal boundary condition for local case, we assume if the diffusion only takes place in the omega, then it just means whenever, how to say, so in this case, so when the diffusion is only take place in omega, so when suppose so x here, for example, x here is in omega, and y, if y is outside omega, then the probability becomes 0. Therefore, this expression is changed to this one. So this corresponds to the normal boundary condition. Then for the Dirichlet boundary condition, impose this actual condition. The population density is always 0 outside omega. Okay, so this is the non-local operator for the corresponding Dirichlet boundary condition. So this is a general situation. Then there's actually a lot of studies related to these topics. Here I list some names of biologists and mathematicians in these directions. Cantrell, Kostner, Colville, and Yuanlou, Martinez, just some names. Okay, so then next, because in the model I want to study here, it's a simplified model. I want to show you what's the meaning of this simplified model. So here, let's come back to the general case and assume in a one-dimensional. Then the alpha. First, we choose this distribution probability alpha to be a function which only depends on the distance between x and y. So it's a function k of x minus y. Symmetric. Also, we assume the total integration is number 1 since it's a probability. Moreover, we also assume when x and y, when they are close, the probability is non-trivial. So here comes this assumption. So everything is very natural, right? Then we modify this k of x. Introduce a parameter capital L, which represents the movement distance. So here, this capital L becomes this operator. Now formally, when the movement distance capital L is very small, just by the expansion, you'll see capital L of U can be approximated by the random diffusion case. Well, if this capital L is very large, also moreover, we assume some periodic assumption on U, then this operator can be rewritten in this way. The blue part I mark here formally goes to the integration of K in the whole domain, which is number 1. So I have this form. So this kind of non-local dispersal corresponds to the case with very large movement distance, like the other extreme. Okay, so here's the meaning. Now let's compare some properties here. Before I do some comparison, I should also show you some known results. Then we compare the quantitative properties of solutions. For local models, there always exists a unique positive steady state. Moreover, the total population approaches the total resources when the diffusion rate goes to 0 or goes to infinity. This is some known results for local models. There's an important property here, which also motivates our studies. Since we assume m is non-constant, based on this equation, there's a very important observation. Divide both sides by theta, and do the integration to both sides. You can easily say that the total population is always bigger than total carrying capacity. So these are some basic properties for this model. Similarly, for the non-local model, we have very similar results. There exists a unique positive steady state, and the total population goes to total carrying capacity when the diffusion rate goes to 0 or infinity. Also, in the intermediate range, total population is always bigger than total carrying capacity. Here's some studies related to this model. I just want to mention one thing. Compared to the local models, in the studies of the non-local models, lack of regularity is a very typical issue. Okay, this is just one thing I want to emphasize. Now let's take a look at some interesting question. As we know already, for both local and non-local models, in the intermediate range, the total population is always bigger than the total carrying capacity, and an approach to the total carrying capacity at these two ends, right? Now what happens in the intermediate, in the middle? That's the main question. Here are two specific problems I try to show you now. First, how about the dependence of population size on dispersal rate? To be more specifically, as given m of x, given the carrying capacity, as the diffusion rate d or b, as the diffusion rate d varies, is it possible? What does this curve look like? Is it possible for the total population to have more than one maximum? That's the first question. Here's some answers, some partial answers. For the local models, it's possible. When the carrying capacity is the perturbation of some constant, it's possible for the total population to have more than one local maximum as d varies. That's for local models. For non-local models, so far we don't have any counterexample. And what we can show is when the ratio between supremum of m and the infimum of m is less than some constants, the curve, the total population, only admits one maximum. So the curve looks like this. So my point here, actually we also try some numerical simulation which indicates that for non-local model, it only admits one maximum. Okay, that's a difference. So at least based on this partial result, you can see something different already. When the carrying capacity is a small perturbation of a constant, then this assumption will be satisfied, right? So in this case, local models can have more maximum, but for non-local models, just one. Okay, here's
So funny. So more than one is no less than one.
More than one.
More than one is at least two.
More than one, no, I don't know how many.
But at least.
At least two, yes, at least two. Yes, more than one. Yeah. because let me see, it's always bigger than this line, so at least 1, right? So we just don't know how many.
The local maximum.
Yes, local maximum. Not global, just 1.
One, but the local maximum is more than.
Yes. For the global maximum, it must be achieved somewhere in between. Yeah, for local maximum, we don't know how many.
How many? But at least 2.
For local, yes. For local case, yes, at least 2.
Okay.
Yeah, yes. Okay. Another question, also related to that graph. It's about the ratio of total population over total resources. Again, as we know, let's define this term. Total population over total resources. And because we know this is always bigger than 1. And when d goes to 0 or d goes to infinity, this actually approaches number 1, right? So the question is it possible for this number, is it bounded above independent of m? That's the question. So for any given m, based on results so far, we know it's well defined. It must be a finite number. But is it bounded above independent of m? If it is, what's the optimal bound? For the local case, there's a conjecture by Professor Wei Mingyi. He said his conjecture is it is bounded above independent of m, and the optimal bound is number 3. So also similarly, we ask what happens to non-local case. Just say, actually this term do play an important role in characterizing the global behavior of solutions to the 2-species computation models. Here's also some partial results. For local models, recently my colleagues and I, Xueli Bai, Xiaoqing He, and I, we verified Ni's conjecture. It's true that the optimal bound is number 3. But for non-local model, there's no optimal bound. So here's the result and some remarks. First, for the upper bound, for the local model, the upper bound number 3 cannot be achieved in the L-infinity function space. In particular, if we choose the carrying capacity in this way, somehow it concentrates at one point. If we choose it in this way, this will give us the upper bound as epsilon goes to 0 for both local and non-local case. For local case goes to 3, for non-local case goes to infinity. When n is bigger than 2 for the local models, so far the numerical simulation indicates that it's possible for the ratio to be bigger than number 3, but there's no conjecture or any results in this direction yet. Okay, so now we see something different. Quantitative properties, there is something different between local and non-local models. The last model is quite different. It's an activator inhibitor model. This is the so-called the German-Hart. This is a famous German-Hart model, which models the regeneration phenomena of hydra. There's extensive studies dedicated to this model since 1990s. Just in this talk, we just try to compare the German-Hart model and its shadow system in terms of the very fundamental properties, global existence and finite blow-up phenomena. See what happens. In the German-Hart model, if we let one of the diffusion rate, D2, goes to infinity, formally, I should say, I should say something more about this model. So in this model, U and V, U is the activator. The U is the activator, while V represents the inhibitor. And the PQR is some parameters here. So a natural assumption here is there's some condition. P minus 1 over R less than Q over S plus 1. This is a very important assumption because this model is formulated based on Turing's idea diffusion-driven instability, which indeed is reflected by this assumption. So, okay, now mathematically, when the diffusion rate before D2 goes to infinity, formally you can show v of xt will approach to a function kc of t, which is independent of the spatial variable, and this leads to the so-called shadow system. This idea was initially proposed by Kiner, and the studies for the shadow system becomes usually is regarded as first step in studying the original German-Hart system. But however, the dynamics of the German-Hart system and its shadow system are quite complicated and far from being understood at this time. So in this talk, we just focus on these two properties and see what happens. So I'll try to show some comparison again. So first, let's take a look at the results for German-Hart model. Here's two things we try to characterize. The first situation is when the ratio P minus 1 over R is between 0 and 1, the solution exists globally for all positive initial values. So only global solution here. Then the other case is it possible to choose some proper initial value such that blow-up solution exists? That's the other situation. Now for the other situation here, this is the unknown regime. So far, there's no result here. But when this ratio P minus 1 over R is bigger than 1, even for the kinetic system, blow-up solution exists. Therefore, the blow-up solution does exist for the German-Hart system as long as you choose the proper constant initial values. Okay? So this is a critical case for these two situations. Always global solution or blow-up solution does exist. Now, what happens to the shadow system of German-Hart system? Well, it's quite different. Here's the result. If this ratio is less than 2 over n plus 2, then always global existence. Moreover, actually, even for the critical case, it has been proved always global existence for any positive initial values. While when P minus 1 over R is bigger than 2 over n plus 2, so far, under some actual conditions here, we can show there exist finite blow-up solutions. Well, it's not there's still some regime opened so far, but under certain conditions, we can reach this critical value 2 over n plus 2. So when it's bigger than 2 over n plus 2, under suitable choices of initial values, the solution does blow up in finite time. Here's a quick summary. You'll see something dramatically different here. For local models, for the German-Hart models, the critical situation is P minus 1 over R equals 1, while for the shadow system, which is non-local, then the critical value becomes 2 over n plus 2. So that's my point. Okay. Some intuition about the results, because if you take a look at these two models, local case and non-local case, as I mentioned before, U the activator, V is the inhibitor. Then in the local case, they interact with each other locally. So the inhibitor can inhibit the growth of U efficiently, right? So I should say in this way, when U is large, it activates V, so V becomes large. Then they can inhibit the further growth of U. Somehow they interact each other locally. However, for the non-local case, KC, it's independent of the spatial variable. Therefore, no matter U is large or small, the KAIST plays the same role. So KAIST cannot inhibit the growth of U efficiently. Okay, that's why it's more easy for the non-local model to blow up. Okay, that's all about these models. I hope that's not confusing, but I'll briefly explain some ideas in the proofs, just some observation I had so far. So first, for the genetic model, instead of the genetic model, we can consider a more general non-local model. You'll see there are some property which is well known for local models, like a comparison principle and the properties of omega limit set, which are already known for local models. However, for non-local models, the situation is not always true. For the comparison principle, there are some actual conditions here. When these conditions are satisfied, we still have comparison principle. And for the omega limit set, for the properties of omega limit set, we need to assume there exists a Lyapunov functional, because it's not always true. Fortunately, for the genetic model we consider here, these two assumptions are satisfied. Therefore, lots of methods applied for local model can be applied here, like upper-lower solution method, degree method, things like that. They work because of these properties. I think I'll skip some details, but I just want to show you, although we try the method known for local models can be applied here, but still we'll have some actual difficulties, mainly caused by the non-local term. The main reason here is the lack of regularity. We can see maybe a very quick case here. When we try to show the non-existence part, we argue by contradiction. We assume like when dk and bk are both very large, there always exists a non-trivial steady state. Then we try to have a contradiction, right? During this process, you will see when we assume dk goes to infinity, then divide both sides by dk. Then what happens here? This will be divide both sides by dk. You will have the rest will be bounded. Then you can apply elliptic regularity. You will have very strong convergence of uk in C2 space. However, when the rate between the non-local term goes to infinity, there's no regularity at all. So the situation becomes more delicate. So that's about also for local stability. During the analysis, we have to handle something related to non-local eigenvalue problem. I'll skip that part. And so for the ecological model, because we only have some partial results, so I want to show you where we have difficulties here. First, it's about the dependence of population size on dispersal rate. For this simplified non-local dispersal, we can have this elementary expression, very explicit expression for the total population, right? Then we can carry on some calculation. So that's what we try to do here. Then if this simplified non-local dispersal is replaced by this generalized dispersal, we have no idea how to express the total population properly. So that's why we can only handle this simplified case. And also for the ratio of total population over total resources, again, in the one-dimensional case, so everything is in one-dimensional case, then we'll have a way, so we divide both sides by theta and do the integration. We have this expression. But here, we can estimate, point-wisely estimate theta prime here. And to show the right-hand side actually can be controlled by 2/3 of the total population. Just the computation strongly relies on the one-dimensional case. That's why we can only have this result for the one-dimensional case. We can have some point-wise estimates here. So there's no clue in higher dimensions. The last case for the shadow system Guerin-Hart system, you see there are some, even from the fundamental properties, global existence and finite blow-up solutions, we see some serious discrepancy. There's a reason for that. Because this is the activator-inhibitor system, there's no comparison principle. So things are dramatically different. You can see maybe this is a system, let's see it more clearly. If we choose the parameter PQIs in the proper way, and this system can be converted into a single problem involving non-local terms. For this one, you can check it can be shown easily that there's no comparison principle for this one. So that's why we just have very different properties for the qualitative properties. Also for this model, even for this simplified single model, so far I don't know the existence of Lyapunov functional. So that's difficult for handling this case. And I think I'll skip the proofs, and at the end, I just want to say, based on our studies for the previous 3 models, we observed that lack of regularity or lack of comparison principle are very typical issues during the studies. Then there are more problems to do. For the genetic model, the uniqueness of steady states is still unknown from both local and non-local case. And for the ecological model, as I explained, for general non-local dispersal operator, we have no idea how to study those quantitative properties. Then for the shadow system, there's some open regime still left. I think that's all. Thank you very much.